Okay, hello everyone. Welcome to More Bugs and More Places. I appreciate the difficulty many of you may have had attending such an early talk given the parties last evening. Sorry. I appreciate the difficulty many of you may have gone through attending an early talk given the parties last evening. Let's start off with an introduction. My name is David Kane Parry. I'm a principal security analyst with the Leviathan Security Group. I'm not going to give you the elevator pitch, but if you're interested in what we do, you can find out more information about us at leviathansecurity.com. I'm also going to be a Hacker Court expert witness. So if you're interested in the technological and legal issues surrounding criminal wiretapping, you'll want to check out the Hacker Court later on at 3:15. I don't remember which room it's in now. So I know there are many here that spend all day long thinking very deep thoughts about security, but there are many more every day where security is just one of their responsibilities in their day-to-day jobs. And so I think before we start talking about mobile security, we need a little background here on reflections on trusting trust. If you're already aware of the paper, then that's good. We're just going to try and cover this quickly for the folks who may not be aware. Back in 1983, Ken Thompson and Dennis Ritchie were awarded the ACM Turing Award for their work in OS theory and their implementation of the Unix operating system. In his acceptance speech, Mr. Thompson described his college day amusement of competing with his friends to design the shortest program possible for self-replicating. That is to say, an application that once compiled and executed would spit out its own source code. He then proceeds to demonstrate how using this principle, it's possible for him to insert a Trojan into the C compiler, such that every time the C compiler detects that it's compiling, say, the login program, they would automatically insert code that would be compiled and insert a backdoor password into the login process. So the moral he goes on to explain is that you can't really trust any code that you haven't actually written yourself entirely, including the compiler or the interpreter that the code is running in. So where does that leave us? Well, we can't just give up on this whole computing thing, so we accept certain risks. And one of those risks is that, well, yes, the SDKs that vendors are shipping aren't really likely to have those kinds of bugs in them. But that doesn't mean that the vendor is the only one who's going to try and ship you the SDK. So how can we trust the SDKs that we're about to install? Well, there are a couple of technologies that help increase the level of trust. You've got SSL and TLS protocols and signed binaries. The SSL and TLS protocols help ensure that you are communicating with the individual you believe you are based on certificates that they provide that you can validate with a third party. The same kind of system is in place with signed binaries. The binaries are provided with a certificate that you can also validate. So you would expect, given that these two technologies are easy to implement, that they would be just about everywhere when it comes to distributing SDKs. But that's not necessarily the case. For the BlackBerry SDKs, you're actually in good luck. They use SSL and TLS for distribution, and their binaries are signed with a valid certificate. For the Android platform, they don't use signed binaries. They only use HTTPS. But there's an interesting bug, at least for the SDK distribution that runs on Windows, where they have had the issue often enough that folks can't download the APIs and documentation that their setup program installs via HTTPS and allow the user to just use HTTP instead. Windows Phone and iPhone SDKs, they use signed binaries, but they don't use HTTPS for any of their distribution. So you might be wondering, well, what if there's a bug in the SSL and TLS protocols or in the signed binary distribution? And that might very well be the case, but that's not really within the scope for the talk that I'll be talking about here. So I'd like to make a quick note about Eclipse. Eclipse is the officially supported IDE for both the BlackBerry environment and the Android environment. Eclipse itself isn't shipped using any secure protocols or any kind of signed binaries, but the Eclipse plugins themselves may be. You can install plugins via HTTPS. Those plugins can be signed. For BlackBerry, BlackBerry installs its plugins automatically from its own installation media, but they're not signed. Android will install those plugins using the HTTPS facility, but they're also not signed. And actually, when you're doing this, an error will pop up from Eclipse saying, hey, wait a second, these plugins you're trying to install aren't signed. What do you want to do? If you're happy-go-lucky, you can go ahead and click it, but in general, it's not a great idea to be training your users to dismiss their security warnings. So let's talk about some of the common features that all of these platforms are going to provide developers. The first one that comes to mind, of course, is sandboxing. Sandboxing is a cute way of describing how applications are put into their own directory with their own usernames, and they can do whatever sorts of damage they want to do within that area, but nothing they could do could possibly hurt any other application on the system. If they want to be able to reach outside that sandbox, they're going to have to use the platform-provided APIs. They're going to be very careful about what resources those applications can access. APIs, that are used exclusively for accessing, say, the mobile phone user's photo collection, the mobile phone user's media collection, contacts, so on and so forth. Let's see. Sandboxing is a useful security mechanism in the short term in the event that it prevents you from accidentally compromising another application. But over the long term, we've seen with other sandbox-like technologies that eventually someone will find a way to break out of it. And so when you're developing applications, it's careful to keep in mind that the sandbox is to protect your application, protect other applications from yourself, but not protect your application from the other ones on the system. If you are doing any sort of persistent storage into the file system, you need to be careful to validate that information just as much as if you were in a desktop environment where other applications could just as easily mess with your state. The other common feature that these mobile platforms provide are the ideas of capabilities or permissions. Basically, applications shipping with metadata describing that the privileges that those applications need to work on the phone, separate from any kind of concept on the desktop you have of a regular user versus administrative user, its capabilities and permissions break down more along the lines of, can this application access the internet? Can this application access the camera? So on and so forth. There are a couple of ways these capabilities or permissions are defined. In the BlackBerry environment, these capabilities are defined based on the code signatures the application is shipped with. RIM requires a $20 processing fee for applications that want code signatures that allow them to access export-controlled crypto functions, access functions for saving information to the phone. And they say that this is really just for monitoring purposes. They're not doing any kind of actual security review of applications in the process, but then in the event that someone is found to be distributing malware, they can revoke the certificate and the application won't be executed. There's an especially interesting use in Android that we're going to be talking about later, where the capabilities don't extend just out into the system environment, but also between applications and between application subcomponents themselves. These capabilities also exist on the iPhone platform, but they're not developer accessible in the sense that the only capability that isn't provided by default to iPhone applications is to be able to use the location service. Every application can request to use it. The user is required to either accept or deny it. By default, most applications all have the same capabilities there. Apple themselves have the ability to grant additional capabilities to applications that go through the application approval process for the application store. But from the developer side, you don't really get to ask for anything more because there's really not anything more you could ask for. So we've talked about some of the common features that mobile platforms have. Now I'd like to talk about some of the common threats the mobile platforms have. Unique threats for mobile platforms as opposed to the desktop or server environment. The first one that comes to mind is that the issue of doing secure wipes in a mobile environment is difficult to impossible. Mobile storage is primarily based on flash media or secure drives, and those flash or secure drives use wear leveling algorithms to make sure that specific sectors don't get worn out faster than others. Unlike your typical storage media where you can read and write a 1 and 0 to a specific sector over and over again and not necessarily degrade the quality of the media, with flash or SD, if you tried to do that over and over again, the entire media would become unusable very quickly. So these wear leveling algorithms ensure that over time, no one sector becomes more used than any other. It makes it difficult to do secure file deletion in that case because there's no real way to guarantee that the 1s and 0s you'd like to write to one specific sector will actually occur on that specific sector because the wear leveling algorithm will intercept that. So you have a couple of options if you need to do secure file deletion on mobile platforms. One idea is that if you have the ability in your deployment in the application use case to fill up the entire disk, then you can ensure that when you remove that file and write back to it, that the only sectors left are the sectors you have in mind. That's not going to fly in most cases. So a good general policy to adopt is that if you have information that you're saving to disk that you expect at some point later on is going to be wiped, a safer approach is to make sure that it's stored encrypted. You don't have to worry about not being able to do secure wipes correctly, because in the event that an attacker gets access to the device, the only way they'll have access to the data is if they get access to the key. Another common threat for mobile devices is geolocation. Just about all of these devices come with GPS receivers in them, and/or they try and do triangulation via cell towers, or do guessing via DNS based on the provider that they have access to. So there are a couple of notes to keep in mind when you're using geolocation services. The first one is that depending on the application you're developing, if you consider stuff like the longitude and latitude of the current user as a private information, geocoders typically don't use SSL protocols. You can, for a fee, I believe, get one from Google that will do SSL, but I don't believe that it's natively supported in their API for the Android API. Another note there is that the API keys are based on the MD5 hash of the certificate that you're using to sign your binary. That's not a significantly pervasive threat, but MD5 collisions are known to happen. I don't know who would go through the trouble of doing a collision on your certificate just so they could get your API key, just so they could exhaust the number of requests that your users can make, but it's something you might want to keep in mind. Another issue that comes up is, and we're going to be talking more about how intents are resolved in Android. But if you're using the Android platform, you're dependent on location providers to provide information to you about where the user is. And depending on what other applications are registered on the device, whichever application claims to provide the highest accuracy is going to be the one that you're getting your information from. It may not necessarily be the one that you want it from, and so a certain amount of trust is involved and/or validation of the information you're getting back. And finally, a lot of people don't consider that users may consider location data private, and you should take that into account as far as when this information remains resident in memory, when you're writing it to disk, what is the appropriate level of privacy for this information, because some folks would be rather upset if it were revealed. Another common issue, independent of the platforms, just at a cellular level, is the security importance of the IME and the IMSI. The IMEI is a unique identifier that identifies the specific device on the network. And the IMSI identifies a specific subscriber. Usually it's associated with the SIM card on a GSM device. So a subscriber can take the SIM out of one device, move it into another, and the network still knows this is still, Bob Jones, but he's on a different phone now. You have the ability to request this information from the phone, but they're really so dangerous that you really shouldn't consider saving them. And in the event that your application is required to transfer them in any context, you make sure that that's encrypted. So the last common threat I'm going to talk about here is forensics. Mobile phones, unlike your desktops or laptops, are much more likely to go missing or be stolen. And when it comes to physical security, I think most of us with a security background understand that if you own the device physically, then you can own the device every other way. So designing your application to be resistant to contexts in which there is an attacker who has complete device with the control is something to keep in mind. Some devices are actually better equipped than others to handle situations like this. An attacker who presumes that a remote wipe facility is available on the phone can take steps to make sure that the phone simply won't receive that self-destruct mechanism. I believe earlier versions of Windows Mobile, which I won't be talking about here because Windows Phone is coming up next, but at least in previous versions, and I would expect in the upcoming version, has a facility to have a heartbeat mechanism in the event the phone can't establish a regular interval connection back to some predefined corporate server. It will also self-destruct. So it's a little harder for an attacker to maintain that control, but it's still possible. Once the attacker has full control of the device, not only are they going to be going after the data that's on it, but they also may be looking at the applications that are installed. If you have special custom applications you're deploying internally to your employees, you can try to obfuscate certain information in it, but it's only going to get you so far because the attacker now has the device and they have as much time as they want with it. So I've talked about some of the common issues here. I'd like to move on to platform-specific issues. Let's talk about the BlackBerry platform. Just at a high-level view, they've sold about 10 million phones by now, which makes them the largest smartphone vendor in the world. Interestingly enough, their smartphone deployment doesn't exactly line up with the number of applications that are currently available for it. Applications aren't required to be available on RIM's app world, but at last count, there are over 2,000 apps there. Compared to some of the other platforms we'll be talking about later on, that's quite a small number, but certainly with the upcoming release of BlackBerry 6.0, I'm sure RIM is looking to change that. Something to keep in mind is BlackBerry is primarily a Java ME environment, which is to say that it's kind of like Java except where it's not. BlackBerry has specific APIs that they're going to be providing, and we'll be talking about those in the next few slides. So one of the first things you'll be looking at for any kind of application these days is storing some information. The BlackBerry provides 3 separate APIs if you have information that you need to persist past the lifetime of your application, past the lifetime of the device being rebooted. BlackBerry has a persistent store and runtime store, which is flash-only memory. They implement a JSR 75 file connection, which is creating actual files on the device. And with BlackBerry 5.0, you have the ability to create SQLite databases. So for persistent store and runtime store, they're both based on key value pairs that are stored globally. This is one of the unique instances where you'll see a blatant violation of the sandbox paradigm. One of the consequences of that is that keys can't be guaranteed to be unique. An application can set whatever key it wants, and another application may try and set the same key if it exists. There's going to be a collision. If it doesn't, it gets there first, and that can be kind of a problem. So in BlackBerry's documentation, they say, well, the polite thing to do is make sure that your keys are predicated based on the package name of the application you're setting, and then tack on whatever unique value you want there. And then you convert that to a long integer and use that as your key. It's a neighborly practice, but it's not very resistant to a determined attacker who can simply iterate over every persistent object that's been stored and get all of their values. Actually, I'm skipping a bit here, so let's rewind a bit. The persistent objects that get stored in the persistent store also take a second level depth to the objects that get stored. So if you define an object as being persistent, any sub-objects that those objects are referring to are also going to get stored. So you should keep in mind for any particular object that you want to save that it's not referring to any other objects that you want to make sure don't get saved. In the case of persistent objects that are completely defined in terms of built-in objects, those objects will actually remain even after the application is removed. In the case you've defined unique objects, those will be removed with your application, otherwise they're going to stay. And finally, in order to make sure that those objects are accessible only by you and not any other application that's on there, you can wrap persistent objects in a controlled access object, which informs the BlackBerry that the only applications that are signed with the same key as the one that created this object are the ones who are going to be allowed to read the values or write new values to it. And this is a nice way if you need to share objects between applications. If you have 3 different applications that are signed with the same key, they'll all be able to access these persistently stored objects. Just as a quick note, the runtime store works exactly the same way, except that any object there won't persist past a reboot. You can do controlled access there. You need to be careful of the object inheritance. But unlike the persistent store, once the device is rebooted, all of those objects are gone. So moving on to file connections. File connections are, let's see, how do we introduce this? The JSR 75 is a platform-independent specification for how Java ME environments should support the use of PIM data and file data. So because Java environment doesn't support using the standard file I/O, you have this concept of a file connection, which is a connection to the file system, but not necessarily to the specific file that you're interested in. So you need to make sure that once you have a connection established, that you don't just start going and doing whatever you plan to do. Make sure that the file actually exists before you start operations. File connections support standard permissions for reading, writing, and read writing. But the caveat there is that enforcement of those permissions is dependent on the security schema that's implemented on the device. Different BlackBerry devices may consider permissions to be enforceable or not. And so that's something to keep in mind depending on if you're targeting specific devices, whether they will honor those permissions from other applications. File connection is really the only suitable choice if you have large files because file connection is the only API that's capable of writing to the SDs in the devices. The persistent object store I talked about before goes straight to flash memory, and you only have about 128 to 256 megabytes there. Make sure I'm getting my notes here. Okay, so SQLite and BlackBerry. SQLite, if you haven't heard about before, is basically a file-based SQL database. I'm not going to spend a lot of time talking about SQL injection here, except for folks who are aware of SQL injection issues. There's APIs in BlackBerry to make sure that your SQLite queries are parameterized. There are three interesting options that you have for using SQLite databases in BlackBerry. When you're creating the database, you can define them as being not encrypted and accessible to any other application, encrypted or still accessible to any other application, or encrypted and only accessible to applications that are signed with the same signature as the application that created it. In the context of the secure wiping situation we talked about before, it's certainly a safer option, whether you're making your SQL database accessible to other applications or not, to make sure that it's encrypted. And that encryption is tied right down to the device. So in the event that your SQL database needs to be ported to other devices, you're going to have a problem there. So there are a few miscellaneous BlackBerry issues that I thought should be brought up. In general, BlackBerry devices, although less so with current deployments, the expectation that a BlackBerry device is going to be required to go through a BES or BIS, that's BlackBerry Enterprise Server, BlackBerry Internet Server, to get out to the internet. If you're doing any kind of SSL sockets in your application, you may ensure that the connection between the BES and the BIS are encrypted to whatever your endpoint is. But if you don't specify that end-to-end required equals true, then there's a possibility that if the BES or the BIS has assigned a self-signed certificate to your device, there won't be any kind of complaints whatsoever. If your device is receiving a self-signed certificate for the BES or BIS, that's a pretty big red flag security-wise. Another thing is that during the application process for receiving the code signatures to access the crypto APIs, the storage APIs, and the other APIs, all of the signing material once your application is provided, once your application is approved, is emailed right back to you. This can be kind of a concern depending on your corporate email retention policies and the ability for an attacker to sniff that communication or retrieve it at some later date. So you need to take special care making sure that once you have your code signing material available to you, that it's cordoned off somewhere. And just as a minor note, the BlackBerry UI provides a password edit field. You're providing a field where the user is entering a password, and instead of displaying the password back to the user, you want to display bullets to mask what the password is. Just in my testing, it seemed awfully slow. This could be just the fact that I was doing everything in an emulated environment. But a user who sees the password field display characters and then eventually overwrite them with bullets may reduce overall trust by the user in your application to perform securely. So moving on to Android, they've sold about 5 million phones right now, which is very respectable given how long they've been around. Over 70,000 apps in the Android market. Like the BlackBerry applications, they're not required to be available on the market. It's just a good general guideline for what's out there. Android is based on the Davlik VM, which is kind of like a Java VM, except not really. And we'll be talking about those differences later on. And there's also a C++ native developers kit for folks who want to write part of their applications in C++. I won't be discussing that here, but the same general issues when using unmanaged code like C++ exist. The release schedule for Android has been kind of hectic. They've been doing new releases just about every 6 months, but they're aiming for doing yearly releases so that developers don't have to always be playing catch up with the changes that they've been implementing. So no real discussion about the Android platform can move forward without an understanding of what activities and intents mean in the Android context. And I'm not sure that I have enough time to do justice to it. I know there's actually a gentleman who gave a talk here last year that just talked about Android. He did a very good presentation. I encourage you to look at that in the archives. But from a 1,000-foot view, activities are ways for your application to do work on behalf of itself or on behalf of other applications. And those activities are launched using intents that are shared between those activities. So an activity will register itself and say, I'm capable of providing GPS information to applications. Or an activity will register and say, I'm capable of providing photos from the user's library. And then other activities and other applications can send intents to those activities and receive photos or receive GPS information and use them in their own application. So there are a few security issues to keep in mind with the intent mechanism. There are a couple of different intents that can be sent. Explicit intents go directly to the applications that you define. Rather than being registered in any sort of sense, the intent is received and automatically delivered, and it's up to the activity to handle it whether they intended to receive it or not. Implicit intents are even more interesting in the fact that there's no specified destination for it. The Android system looks at the intent, looks at the content of the intent, and looks at the registered activities and says which activity is best set up to handle this intent. And which activity is ever best set up, that's the one that will receive the intent. Skipping back a bit, implicit intents can be filtered. You can define an activity that says, I'm only going to handle intents that look like this, don't send me anything else. Explicit intents can't be filtered in any way. You'll receive their intent and you'll have to handle it, validate it, or discard it as your application requires. As far as the implicit intent resolution, there are a couple of interesting issues that pop up there. First of all, as an attacker, there's nothing to stop me from developing my application and saying my application is the best for doing exactly what your application needs it to do, instead of, say, the native Android components, which don't have any kind of higher authority in the resolution process. The resolution process doesn't say, is there any native component that can handle this? If not, then let's look at the third-party applications. It's blind in that way. So if my application is better registered to handle your intent, then it's going to handle it whether you want me to or not. So you need to be careful with the information that you're sharing with third-party applications in your intents. You also need to be careful to validate the information you're getting back from those intents. As a follow-on issue there, perhaps an application isn't able to register itself as the best to circumvent your application. But it can certainly register itself to be as good as some other component that you're hoping your intent goes to. And what happens in that case is that the user is presented with a pop-up. The Android system says, hey, I found 2 different applications that can handle this intent. Which one do you want me to use? And so now you're trusting the user to make the right decision. And as the third-party application developer, I can try and trick them in any which way I want. I could present my application to display the same name as your application, and they won't really know which one to touch. Also, with the intent situation, since you're not exactly sure where they're going to go to, I could, for example, man in the middle your intent request. I'll take your intent request, just make a note of it, and pass it on explicitly to another component that I know can handle it better. I'll get their response, send their response on to you, and in that way I'll man in the middle your intent activity. So there are a few features in place that can help limit the fallout from that situation. Permissions in Android help you restrict who can call into your code. Applications may send you intents that you don't want to handle. Perhaps you only want to handle intents from other activities in your application or other activities in other applications that you've written, but not activities from other applications that you don't even know about. And so what you can do at the activity level is define an activity to say, here's a unique permission that this activity has. And I'm only going to enter intents from other activities that have the same permission. Well, technically, there's nothing to prevent other applications from say, I also require that permission. But what you can do when you're defining that permission is say, well, not only is this a unique permission, but I don't want you to grant this permission to any other application unless they're signed with the same key as me. You can also implement that kind of restriction on broadcasters. Broadcasters, like the intent system, is a way for applications to send messages to each other, except it's only about state changes. So an application may say, I received a new RSS feed and send a broadcast intent to every other application because there are other applications that may want to consume that RSS feed. Well, you can restrict who you're going to receive broadcast messages from if you don't want other applications to mess with how your application performs given a state change in another application. Content providers are a kind of specialized activity that are just for exposing databases to other activities and applications. And they have a second level of permissions that you can implement, giving other activities only read access, only write access, or giving them read and write access. Although, as already been noted, if you have write access to a database, given enough persistence at specialized write requests that you make, you can effectively read information out of it. And so just be aware that setting write-only permissions doesn't necessarily mean that other applications won't be able to glean access they could read out of your database. So persistent storage in Android. Unlike BlackBerry, Android actually can use the standard Java I/O calls. So I'm not going to be talking about security issues there that are already well known. But there are some unique facilities that Android provides as far as persistent storage goes, especially as regards preferences that are being saved. There's a shared preferences class that will allow you to share preferences just for your components and not for applications. If you have, at the activity level I was talking about, if you have a specific activity that wants to remember some information, you can save that information just for that activity, and no other activity will be able to have access to it. Another thing to keep in note is that with the open file input and open file output calls, those calls are restricted to the application's root directory exclusively. So if you have information, perhaps you're doing file-based information where the user's providing input, and you don't want to bother with making sure there's no directory traversal going on, you can use those calls that will automatically throw exceptions if there's any kind of traversal characters in it, because they're designed only to use the root directory, no subdirectories, no parent directories whatsoever. SQLite is a bit different than BlackBerry. You don't have the kind of encryption options that BlackBerry provides. You don't have any option of making it available to other people natively except through the content providers. So it's restricted just to your application alone. Excuse me. But like I said, you can use content providers between applications to share that kind of information out. So there's some miscellaneous issues that I thought I'd talk about here. There are the native applications you're developing for Android, and there's also the concept of widgets. These are applications that are running on the home screen rather than a separate application. So something to keep in mind if you're developing widget applications is that since widgets are actually hosted as part of the home screen process and not their own process, that they're inheriting the permissions of the home screen process. And those permissions are generally much more than what the specific application may have defined as being required for them. So as the saying goes, with great power comes great responsibility. So making sure that with the new permissions you have, that you're resistant to attackers trying to coerce you to use permissions that you otherwise hadn't intended to use in the first place. Along the same lines, the Bluetooth admin permission will enable your application to automatically turn Bluetooth on or off without any kind of prompting to the user. Normally, applications that define Bluetooth privileges have that privilege, but the user is still warned, hey, this application wants to turn on Bluetooth. Do you want to allow this? With the Bluetooth admin permission, that's not going to happen. And finally, there are a couple of ways to get pictures on the Android platform. You can either implement the camera class if you have the camera permission to use it, or you can just send an intent to the native camera application and get camera data from it. The camera application by default injects EXIF information into it, which may include location data. So you may want to be careful to give your user the option of scrubbing that information out of it. Or if you're calling the class, that doesn't automatically inject that information, tell the user, I didn't put any EXIF data in here, would you like me to? And then proceed as they wish. So moving on to Windows Phone. Windows Phone 7 still in beta, so they haven't sold any phones yet, but I'm sure they're hoping to sell a few. I don't have one to test with, of course, so all of this is based on my use of the emulation environment. It's hard to say how many applications are out there, given that technically you may consider some pre-existing Silverlight 3 or 4 applications as being Windows Phone 7 applications, because Windows Phone 7 is based on Silverlight. The environment that they have there is kind of a hybrid between Silverlight 3 and Silverlight 4, with even more changes to make things more confusing for you. It also supports the XNA environment, which is used widely for developing Xbox Live games, but I'm not going to be talking about that here because it's primarily gamer focused. They released the CTP in April, the beta in July, and maybe they'll have a final in October. An interesting thing here is that with the release of Visual Studio 2010, it is technically not possible for you to develop Windows Mobile 6.5 applications anymore. You have to retain your older versions of Visual Studio because Microsoft just isn't going to support it anymore. So isolated storage in Windows Phone. Since it's all based on Silverlight, it's using Silverlight Sandbox. Oh, excuse me. All right. So Silverlight Sandbox uses the same kind of principle everyone else does, which is you have your directory, you can write to that directory, you can do all sorts of damage into that directory, but if you try and reach outside of it, you're going to get stopped. Let me rewind a bit. Most of you may know Silverlight as a browser plugin, but one of the more recently introduced features is the ability to run Silverlight controls outside of the browser. And outside of the browser, these Silverlight applications have desktop quotas that limit how much information they can store in their isolated storage. In the typical environment, they get a 1 megabyte default quota, but they could ask the user if they need more, and the user could give them more if they really wanted to. In the Windows Phone environment, quotas don't exist anymore because the assumption is that every application is running outside of the browser. The concept of a quota doesn't make a whole lot of sense. That's not inherently a bad thing, except if you're putting an application from a pre-existing Silverlight environment into the Windows Phone 7 environment, and you're counting on that quota enforcement to limit the amount of damage that could be done. On the desktop, a file-based DOS on your application can't do much damage if you've only got a 1 megabyte of space. But in the Windows Phone 7 environment, if a user or application is able to use up all of your storage, users are going to get very unhappy very quickly and just automatically remove your application. So if making sure that when you're doing persistent storage on Windows Phone 7 that you're keeping mind of how much you're using. And just as a final note, since all of the applications of Windows Phone 7 are running out of the browser, there's no concept of having a site origination. When Silverlight applications are running in the browser context, there's a specialized isolated storage that allows Silverlight applications that all originate from the same site to establish an isolated storage that they can share between. Since there's no sites in Windows Phone 7, there's no more site storage, so you don't have any kind of isolated storage. You could share data between applications. So capabilities in Windows Phone, it's akin to Android's permission system as far as defining can this application access the internet, can this application access the camera, but that's pretty much where it stops. It doesn't have the same facility. For example, saying that particular methods can only be accessed under certain conditions. In the Windows Phone 7 environment, if you're creating a new application, the default is that you automatically request all of those permissions. If you're not aware of that, your application may be requesting a whole lot more permissions than you need, and those may eventually be abused down the line. Unlike for Android templates where no permissions are requested by default, and it's up to you to incrementally request them. In the Android system, it's known that for any particular permissions your application is requesting, the user is presented with a pop-up saying this application is requesting these permissions, do you want to grant them? I don't know whether the same kind of system will be in place for Windows Phone 7. All I know is from using the emulator environment, I know the emulator environment doesn't much care what permissions I'm requesting. So there's some miscellaneous issues for Windows Phone 7. The largest one, of course, given the hybrid nature of the Silverlight environment and the unique changes that they've made for Silverlight Mobile, is that documentation, good documentation, is really hard to come by. Depending on methods that you're implementing, they may not behave the way that they're documented. And so that's something that a real rigorous QA process is going to have to shake out if you're already developing Windows Phone 7 applications. Many methods that operate just fine in the environment still may return slightly different values in Silverlight Mobile. For example, let me see, I made a note here. I think it was get path directory will return an empty string if the path happens to have any leading white space in it for some reason. There was another, I think it was, there was another call I don't remember the name of that wouldn't throw any kind of exception even if the path name was too long for the maximum path size. Another thing to keep in mind is that many applications, if they still throw exceptions under conditions that they ought to, may be throwing different types of exceptions. And so the handlers you have set up to handle the exceptions that you expect may not be the exceptions that are being thrown anymore. So again, a real rigorous QA process is going to shake those out. As a final note, DTD parsing is completely taken out of Silverlight Mobile. There are some valid security concerns there, given the ability to force the application to request DTDs over and over again. But rather than providing the facilities they have in other versions of Silverlight where you can use it at your own risk under certain circumstances, being careful to catch exceptions, they've simply taken it all out. And so in the event you're developing an application where you have to use DTD parsing instead of switching to XML schemas or something, you're going to be forced to write your own. And we've seen more often than not when folks are forced to write their own implementations of commonly available API functions, that it's going to wind up a lot more insecure than if they had just had the native facilities available to them. So moving on to the iPhone. They have sold over 8 million phones, which I think makes them the second largest. But they have the most registered apps, over 200,000 apps available in the App Store. And that's not even counting the applications that are available for folks who have jailbroken their phone. The iPhone environment is primarily Objective-C 2.1 based, kind of, which we'll get into later. iOS 4.0 was released just this month. And they've been doing major software and hardware releases just about every year. So memory management in the iPhone. The iPhone is unique compared to the other platforms I've been talking about before because all the applications are on managed code. You're responsible for allocating your memory, you're responsible for deallocating your memory, and unlike the Objective-C runtime on Mac OS X, you don't have any garbage collector to help you out with that. So all of the standard memory management and memory corruption issues that you're used to in unmanaged code on C and C++ are present on the iPhone, so I'm not going to spend a lot of time there. Just be aware that they're there, and you should make sure that you're taking care of those issues. An interesting thing to note for folks who aren't familiar with Objective-C is that you have the ability to release an object or auto-release an object. And auto-releasing is really just a nice way of saying, well, I'm not really sure if I need this object again, so let's put it in a pool, and I'll empty that pool when I'm really sure I don't need it anymore. So if you auto-release an object, it's still leaking until you drain that pool. So if you're using auto-release at all, make sure you're draining your pool in a timely manner. Otherwise, you might as well just be using release when you're absolutely sure. An interesting thing to note about preference storage for the iPhone is that as far as violating the sandbox concept, you have two options for saving preferences. You can do preferences all your own in your application, in your own sandbox, and do very complex settings. Or if your settings are of a more simplistic nature where you have a slider, a few fields, and that's it, you can implement a settings bundle that actually be installed as part of the settings application and run in that sandbox. Depending on the simplistic needs of your preferences, you could go either way, but one thing you might want to consider is given the attacking value of compromising a sandbox where every other application may be saving its preferences versus just your sandbox where you're saving your preferences. Each application is going to have different acceptable risk levels, but it's something to keep in mind that you have that choice. Mac OS X developers who are used to being able to share preferences between applications are used to be able to define suite-based preferences in a separate storage area where all of those applications can read and write from. Because of the sandbox nature of the iPhone, suite-based preferences just aren't supported. But as a suitable alternative, the keychain mechanism works quite well. If you have an application that reads and writes to the keychain based on entitlement, you can share that entitlement with other applications that you're signing with the same key, and the keychain will allow those applications to read and write to the same storage area because they all have the same entitlement. Just as a quick note, the entitlement concept isn't to be confused with the capabilities or permissions things. It's simply a keychain exclusive way to say, I'm an application, I'm able to read or write this value in the keychain. Also, the encrypted nature of the keychain takes off one layer of responsibility of making sure that information stays encrypted. So there are also some miscellaneous iPhone issues to talk about here. Being unmanaged code, the Xcode IDE that you'll be developing iPhone applications in, it can do some static analysis. It'll be able to tell you, in general cases where you're leaking memory or, unconventional coding practices, but it's not going to provide the level of static analysis that, say, folks who have been using Visual Studio are used to for calling out dangerous API calls or other security-related issues. And it's fairly unique, although it's not going to be for Windows. It's not going to be unique once Windows Phone 7 comes out, because they'll be using the same application approval process. Is that in the event of vulnerabilities found in an iPhone application, it can still take, on average, about 2 weeks for Apple to approve and start distributing a new version of the application. So coding defensively is even more important for iPhones, given that window of time that an attacker has to compromise even more targets. And because it's been in the news recently, I'd just draw attention to the fact that newer versions of the iPhone provide a layer of hardware encryption. But this hardware encryption isn't really meant to provide security for the contents of the data in a live environment. It's actually implemented more as a faster, secure wipe. What the iPhone can do is, given a password, encrypt the file system with that password. And then in the event of receiving a remote wipe signal, instead of going through the tedious process of trying to overwrite the entire disk, it simply overwrites the key. So all of the data is still there, it's just encrypted, but technically you don't have the key, so it's secure. Which is to say that you shouldn't trust the hardware encryption for your own application's encryption needs. Make sure that if you have any encryption needs, you're handling those appropriately yourself. So wrapping things up here, on Measure, all of the platforms have their own pros and their own cons. How those pros and cons measure up depend entirely on the background that you're coming from. It's going to be up to you to decide which ones are acceptable, which ones are unacceptable, which ones you can mitigate, which ones there's just no working around given what your application needs to do. It's your own strengths in programming that are going to help your applications more secure, not the platforms themselves. The platforms can only help make things better. They help you be the best programmer you can be. But all in all, there's no going to be perfect security in your applications, but there's going to be just right, depending on your measurements. So I'm not sure how we are on time because the stopwatch never started, but we have plenty of time for Q&A, folks. Oh, 20. Okay. Well, let's see. Questions? I'm sorry, I can't hear you very well. Yeah. Oh, okay, sure. So yeah, just a couple of days ago, the Citibank iPhone application was removed from the store because it turns out that they had been hiding user credentials and bank transaction data on the file system. I'm not sure how that came to their attention, but it's certainly, I believe, a PCI violation, which is why they got so concerned about it. Even if they had been storing it in encrypted fashion, they could have been in trouble there. Certainly the safest thing to do given their environment is if they had saved the credentials in the keychain and on a per instance loading of the application just receive state from the server, then they wouldn't have to worry about saving that information. But it seems they did anyways, and they've learned the hard way that they need to go back and rewrite things. Yep. Sure. Okay, gotcha. So I was just someone who's making sure I clarify that when you're calling auto release on something in the main thread, that it automatically gets released. What were you saying there? For every iteration of the run. Okay, cool. All right. Well, I'm sorry that I finished a lot sooner than expected. I've given talks before where I've gone over, and so maybe I compensated in the wrong direction this time. We've finished with the Q&A here, but I have a question of my own for someone in the audience. This is my girlfriend, Alexandra. She's had the bad luck of having been born so close to DEF CON, but I've had the good luck of her accepting my date request over 12 years ago. So I have a question for her if she would come up stage. Alex? Would you marry me?
I will.
All right.